Hi there, we're in Chapter 8. We're looking at parabolas today. A parabola is the set of all the points x and y in a plane that are equidistant from the directrix, which is a fixed line, and the focus, which is a point that's not on the line. Parabolas come from the intersection of a plane and a double-napped cone. This is a double-napped cone. So we get a parabola when we slice through the cone at an angle. This one is going to make a parabola right here. Later on in the unit, we'll see that we can create circles, ellipses, parabolas, and hyperbolas. This last one here is just two intersecting lines. Then there's degenerate conics, and those are points, a single line, and intersecting lines. So this is an example. A point would be that single point right there, and a line would just be one slice through one of the cones. Anyway, the conic sections can be defined algebraically as the graphs of second-degree equations in two variables. And they, in expanded form, they can look really complicated like this. But A, B, and C are not all zero. We'll see some features that determine what they look like based on their equations as well. Here's a little more colorful picture that I found on the internet. This is the cross-section of a cone. So again, you can see the circle, the parabola, the ellipse, and the hyperbola when you pass a plane through the cones at a certain angle. So we're going to explore by first looking at the, let's go back here. Here we go, I skipped a page. We're going to first explore by looking at the standard form of the equation in that definition, where we said that the distance was here, this distance, from a point on the parabola to a focus point, and then the distance from a point on the parabola to the directrix, which was a second line. I'm just going to label them D sub 1 and D sub 2, and we're going to try to prove this formula for our parabola. So this is my focus point. This is the directrix. We could label those. This point here is the focus, and this line is the directrix. And by definition, we said that any point along the parabola is equidistant from a focus point and from the directrix line. So using a clean sheet of paper, if distance 1 and distance 2 were the same length, and we had distance 1 was the ordered pair 0p and xy, 0p and xy, then I can use the distance formula as x minus 0 quantity squared and y minus p quantity squared. That distance would be equal to the other distance, which was xy and x negative p, or opposite p. So using those two ordered pairs, that would be x minus x quantity squared plus y minus negative p quantity squared. And then simplifying here, we've got x squared plus y minus p quantity squared, and this is 0 squared, and y plus p quantity squared. So without spending too much time, I use the distance formula to say that the two lines segments were equal in length, that the distances were the same. Then if we squared both sides, that would get rid of the square root, and then simplify the terms inside, it gives us here. So if we expand both of these binomials, we've got x squared plus y squared minus 2py plus p squared is equal to y squared plus 2py plus p squared. And then collecting like terms, the p squareds go to 0, the y squareds go to 0, and if we take this negative 2py over to this side, we find out that x squared is 4py. And this gives me a standard form equation for a parabola whose vertex is sitting on the x-axis at the origin, and that's our general form of the equation. Now we could do the same thing if we drew a parabola that was situated to the right or the left and the vertex was also on the origin, but you can see how we could prove that. So in this exploration, we want to label the parabola as a visual for all of the important features that we need to find. So this is the parabola itself, and this is the focus point. We said that dotted line was called the directrix. The y-axis in this picture is our axis of symmetry. This would be the vertex point right here, which happens to be the origin in this case. And changing colors here, the length from here to here is p, and the length from here to here is also p, but it's in the opposite direction. And this p is called the focal length. The focal length. You can tell by looking that the focal length is the distance from the vertex to the focus point. And then if the focal length, this is double, so that's 2p. If you come across here and draw a chord that passes through the focus point with a point on the parabola, on both sides of the parabola, that is called the focal width. And sometimes that focal width in some textbooks is called the latus rectum. And its distance is 4p all the way across from one side of the parabola to the other. But the really cool thing when it comes to the equations is this is 2p and that's 2p to make the focal width 4p all the way across. And you can see we have p from here, from the focus to the vertex, and p from the vertex to the directrix. So it's 2p and 2p across twice. So you want to recognize those patterns. Now this is interesting. While the Greeks defined conics in terms of the intersections of planes and the double napped cone, we're going to study conics as a locus or a collection of points that satisfy some given geometric properties. For example, in our study of parabolas, you learned that a parabola is the graph of a quadratic function, and we could write parabolas either standard form this way or what I call vertex form this way. So we want to tie all of that together. In this way, we're going to look at the parabola x squared equals negative 8y. So we know that this follows the pattern of x squared equals 4py. So we know that the focus is on the y-axis. And the vertex is the origin. And the p, if 4p represents negative 8, then p is negative 2. So we know we've got a vertex at 0, 0, and this parabola is going to go upside down since the p is a negative number. We know that the parabola faces down. So the focus would be at 0, negative 2. So using the idea that we've got the vertex at the origin and the focus 2 units away, the distance for p is 2, so the opposite of p would go 2 units up, and that would give us the directrix. And then we said that the lattice rectum goes from the focal point to P on both sides. So we've got to get a distance of 8, which means we're going to go 4 units to the right from the vertex, from the focus point. 1, 2, 3, 4. And 4 units to the left. 1, 2, 3, 4. So we've got the upside down parabola, whose vertex is at the origin. The directrix is y equals 2, and the focal width was 8. Took the absolute value. So if you could imagine that focal width going through there, it's 4 units this way, 4 units this way, and 2 and 2 for 4 units between the vertex, the focus, and the directrix. So they're evenly spaced out that way for you. Seems pretty easy. So let's give this one a try. This one is a parabola whose center is on the x-axis, and the parabola is going to the left. So we're going to use the formula y squared equals 4px. So the parabola would go to the right if the p-value was positive, and it would go to the left if the p-value was negative. Since our parabola is facing to the left, we know that we have a negative p-value. And then it just becomes a matter of counting. So you can see between here and between the directrix and the focus, we have 3 units across. This is at x equals 3. Then we have 3 more units. So if we were going to find the focal width, we'd go 6 units this way and 6 units this way to find the other 2 points on our parabola, which is off the screen here. So we can tell that our y squared is going to be 4p x, and we said it had to be negative p since the direction of the parabola was facing a negative direction. So our equation is y squared equals negative 12x. And we have that parabola facing to the left. Now, I know in your notes that you have a blank sheet of paper, so you may want to turn off the video and spend some time copying this into your table of notes, and then come back and join me when you get finished. Okay, so now that we have those notes, we're going to look at graphing this basic parabola who's been translated off of the origin. And this is my h, and this is our k, and it's x minus h and y minus k. So h is positive 1 and k is negative 2. And this is where we're getting our p-value. So 4p is in the place of 2, which tells me p is 1/2. So if our vertex is at 1, negative 2, and the p-value is positive, and the form is x squared equals 4py, then we've got a positive p, so our parabola has to open upward. And our vertex is at 1, negative 2, and we're going to go up 1/2, so up 1/2 is right there, and then down 1/2 is right there to get our directrix and our focus. So we have a focus, a vertex, and a directrix with the parabola going this way. And then we want to go 2 units up from the focus point, 1 to the right and 1 to the left. And this is where we get our curve. So we've got 1 here, 1 here, 1/2 here, and 1/2 here. So our focus would be at 1 and negative 1.5. And the directrix is going to be at y equals negative 2.5. And the focal width was 2. and it made our parabola go up. In example 3, this should be example 4. We got a typo here. In example 4, we're going to have the HK value looks like 2, -1. So this time we're going to use the parabola graph and write the equation. Our p-value has to be negative since the parabola is pointing in the negative direction, and it looks like the p-value is 2. So if we go 2 units over, that's going to tell us here's our focus point at -1. So 0, -1, with the vertex at 2, -1. The directrix is at x equals 4. And if this distance is 2 and this distance is 2, then this would have to be 4 and 4. So our focal width would end up being 8, but because it's going this way, it would have been a -8 since it's facing toward the left. And then what do we have to do? Write the equation. So our equation is y minus k, and k is -1. So y minus -1 squared equals -8, that's our 4p value, times x minus h, and h is +2. So this becomes our equation for example 4. And we just have 2 more to go. In example 5, I misnumbered all the way across. Okay, in example 5, we want to find the standard form of the equation for a parabola whose focus is at 4, 0, and whose directrix is at 2. So 1, 2, 3, 4. So our focus is here, that's the focus, and the directrix is at 2. And remember, we said the directrix, the vertex, and the focus, and they're equally spaced. So the vertex has to be at 3, 0. So this would be our HK, would be at 3, 0. And if this is 1 away and 1 away, then the parabola has to go to the right. And if you double that 2p, that would be 2 up and 2 down. So our 4p would have to be 4, and p would be 1. And then we're going to write our equation. So this would have to be in the y minus k squared equals 4p x minus h formula for the parabola to go to the right. So y minus 0 squared is y squared, and 4 times 1 is 4 times x minus our h, which was 3. And we have our equation. Then in the last example, example 6, we want to show that the graph of the equation is a parabola and find its vertex, its focus, and the directrix. And this is not set up very friendly, so we want to reorder it and put it in the right format. So y squared minus 6y, and we'll have to complete the square. And then we'll take the 8x, we'll add 8x to the right side and subtract 17. And then whatever we add to this red box, we'll have to add the same thing on the other side. So back from Algebra 2, when you complete the square, we want to take half of that middle term. So half of 6 is 3, and 3 squared is 9. So we want to add 9 to the right to keep it balanced. So we're adding 9 to both sides. And factoring the left side gives us y minus 3. Whoop, I wrote 6. That would give us y minus 3, quantity squared, And 8x minus 17 plus 9 would give us 8x minus 8. And if we factor out an 8 from the right, that would be our 4p value. So we could get our standard form this way, and then we're going to pull all that information apart. So we're calling this standard form. Standard form. And this is our k, because it goes with the y. And this is our h, and our 4p is right there. So we know that hk is the vertex, which is 1, 3. So our vertex is 1, 3. And we need the focus and the directrix. And like we said earlier in the last example, if the hk is at 1, 3, and our 4p is 8, then p must be 2, and it's a positive 2, and it's in the y squared format, so our parabola is pointing this way. We have to go 2 units to get to the focus. We have to go 2 units to the left to get to the directrix, because the directrix and the vertex and the focus are equally spaced apart. So if this goes 2, and this goes 2, and this point was at 1, 3, then this point has to be 3, 3, because we're adding to the x value here. So our focus is going to be 3, 3. And then the directrix 2 units away would be, let's see, if we were at 1, so we'd go 1, 0, -1. So our directrix would be at -1, since our p-value was 2. And that's the end of our first lesson in this unit on parabolas. See you next lesson.